Last Tuesday was a historic day because we were celebrating the 50th anniversary of a breakthrough in physics, the discovery of the Bell inequality. 1964 was a good year. Higgs and others described the Higgs mechanism. Gell-Mann and Zweig proposed the quark model. Penzias and Wilson discovered the cosmic microwave background. I saw the Beatles on the Ed Sullivan Show. And all of these discoveries still reverberate 50 years later as we struggle to understand physics beyond the standard model, the large-scale structure of the universe. And Bell's legacy is another frontier of physics, also very fundamental and exciting, what we might call the frontier of complexity, the entanglement frontier. Physicists are trying to scale up the weirdness of the microscopic quantum world to larger and larger systems, anticipating that highly entangled systems can behave in ways that can surprise us and illuminate issues in physics and maybe prove to be useful. There's another reason why this symposium is taking place at a particularly auspicious time. The world has never been more curious or puzzled than we are today about a fundamental question: what's inside a black hole? And as Joe has reminded us, we've been struggling with that question for the 40 years since the discovery of Hawking radiation, and yet it's as deeply puzzling as ever. Now, if you follow your Twitter feed, you might see the evidence that we can get some guidance about how to get out of these problems by appealing to ideas concerning quantum information and quantum entanglement, but we're still really confused. And so confused that people can seriously suggest that in order to save quantum theory, we will have to modify it in some way. And so you'll hear people say things like, well, maybe we need a final state boundary condition at a future space-like singularity inside a black hole, or that we require some kind of nonlinear state-dependent map to relate the interior and the exterior of the black hole. So these are radical suggestions, changes in the quantum mechanics that over the years we've gained great confidence in. Now, the idea that quantum mechanics might be an approximation to a more exact theory is, of course, not at all a new idea. And it has aroused the interest of experimentalists for a long time, that we might find limitations of quantum theory by doing laboratory experiments. So even today, experimentalists with increasing ingenuity are trying to test the violations of local realism that Bell pointed out, to overcome the objections of skeptics and critics. Experimentalists are studying cat states, superposition of macroscopically distinct states in a variety of platforms. And we're reaching the era now where we can seriously envision operating large-scale quantum systems, quantum computers, where we can control the evolution of highly entangled states and perhaps perform tasks which wouldn't be possible if this were a classical world. At least we should be able to do that if our current ideas about quantum mechanics are correct. But any program to test quantum mechanics is hampered by the dearth of plausible alternatives. What exactly is it that we're testing? What is it that we're trying to rule out? So, for example, we can consider experiments with cat states. We can do double-slit interference experiments with heavy nuclei or with large molecules, perform spin squeeze states or prepare spin squeeze states in atomic ensembles, study superpositions of the clockwise and counterclockwise circulating current in a superconducting circuit, superpositions of position states for Bose-Einstein condensates, superpositions of motional states for macroscopic oscillators. But who has the biggest cat? which of these ways of probing for some intrinsic decoherence mechanism going beyond environmental decoherence provides us with the best test. Well, we could try to quantify how catiostate is by saying, well, how big a portion of the system would we have to measure in order to collapse the superposition? And then we can ask how redundantly is the information encoded in the system that is revealed by that collapsing measurement. And that would give us a way of quantifying how big a cat is. But that type of criterion still doesn't escape ambiguities and uncertainties, because we might want to choose different ways of decomposing the system into subsystems and get different answers. Or we might want our degree of cattiness to depend on things like how spatially separated are the different macroscopically distinguishable states, or what their masses are. And the real fundamental problem is, in order to say which is the best cat for testing quantum mechanics, we have to know what we're testing. We would like to have some model with parameters and be able to say that as a result of an experiment, we have placed limits on such parameters. So how should we think about possible deviations away from standard quantum theory? Decades of experience suggest that we use something like the effective field theory formalism. Suppose, for example, that I'm interested in theories in which unitarity is not exact. Evolution includes some intrinsic decoherence mechanism at short distances. We can ask whether it's possible that as we coarse grain the system for the purpose of describing the physics at longer distance scales, does that intrinsic decoherence flow away in the infrared so that unitary quantum mechanics is emergent in the long distance limit? And that kind of program immediately runs into difficulties, because typically, if we introduce a little bit of deformation away from unitarity, that's a highly relevant perturbation of quantum theory, and the effects actually get amplified in the infrared rather than decaying away. And not only that, but a theory which has some kind of intrinsic decoherence will, in typical cases, also violate conservation of energy. The intrinsic decoherence heats the system up, and it's not clear how we can consistently couple the theory to gravitation if energy isn't conserved. So these are good objections to the idea of deforming away from quantum mechanics in the way I've described, and I don't have compelling rebuttals to those objections. But let me suggest a couple of metaphors that might guide a way of thinking about deforming away from quantum theory. One is the metaphor of quantum error correction in trying to understand how to protect large-scale quantum computers from the damaging effects of environmental decoherence. We've developed the theory of fault-tolerant quantum computing. And the main idea of quantum error correction is that if we want to protect quantum information from damage, then we should encode it in correlations among distantly separated parts of the system, quantum correlations, quantum entanglement. So the environment may be buffeting the system locally, interacting locally with single particles or small clusters of particles, but those interactions don't cause the information to leak out of the system, because the information doesn't reside in those individual small clusters. The information that we want to protect is almost entirely encoded in the long-distance correlations, the entanglement among the parts of the system. So, in fact, in the early days of quantum error correction, we drew a lot of inspiration from the idea of the renormalization group by envisioning a hierarchy of codes within codes within codes, where the noise occurs at some appreciable rate at the lowest physical level on the physical qubits. But as we advance to higher and higher levels of that hierarchy, the effective noise becomes weaker and weaker. So that at least if the fundamental noise is sufficiently weak to be within a basin of attraction, in the infrared, the system flows to unitary quantum mechanics and the decoherence goes away. So we can ask whether it's possible for nature to have followed that example, weaving fault tolerance into her design so that the decoherence can flow away at long distances. A second useful metaphor is that of a leaky brain. We can think about physics on a brain, which is embedded in a higher dimensional bulk, where, let's say, the overall theory exactly conserves energy and has unitary evolution. But at least at sufficiently high energy, there can be leakage of both energy and information from the brain into the bulk. So if I consider an effective theory describing the physics only on the brain, it will be a theory with intrinsic decoherence and also with non-conservation of energy, but with unitarity and conservation of energy being emergent properties at long distances or low energy. And a theory like that can be coupled consistently to gravity if we couple it to the joint system of the bulk in the brain. So this is an example of what we could call the principle of anomaly inflow, which has achieved greater prominence lately in the development of the theory of symmetry-protected topological phases. We can have a theory in d dimensions which seems to make no sense by itself, but we can make sense of it by embedding it in a higher dimensional bulk theory. So for example, the surface of a topological insulator really doesn't make sense alone, but makes sense if we consider it to be the boundary of a higher dimensional bulk. So this example also illustrates the relation or potential relation between emergent geometry and emergent quantum mechanics. We might imagine a theory in which there's intrinsic decoherence, and in order to make sense of the theory, we use a dual description in which there are emergent additional spatial dimensions in terms of which we have a description which looks unitary and can include gravitation. Now, if we put gravity aside for the moment, we can ask, my collaborator's name got covered up there, David Poulin. Is it possible to find examples of quasi-local field theories which have some small amount of intrinsic decoherence, but which become suppressed at long distances? We can describe such theories in a path integral language, where the path integral represents an evolution law for density operators. And we could demand that the density operator has to remain positive and normalize, so probabilities sum up to 1. And just to constrain the physics further, we could also impose Poincare invariance. And then if we were really talking about a theory in which there is no intrinsic decoherence, the bra and the ket side, the left and the right side of the density operator would be state vectors evolving independently. And the bra and ket variables that I integrate over would not be coupled with one another. But we can include decoherence in the description by adding terms to the action that couple together the bra variables and the ket variables, what I call the dissipator. And we can at least imagine in principle that the dissipator is a high dimension operator whose effects at low energy are, by standard power counting, suppressed. But a theory like that requires, on the face of it, fine-tuning, because this highly suppressed decoherence would not be stable under renormalization. That is, lower dimension operators would be generated under renormalization, which would be relevant in the infrared. This type of theory typically has systems, if it's Poincare invariant, evolve in time towards some Poincare invariant state. And there are two things that generically happen. It may be that systems evolve towards the zero temperature state, the Poincare invariant vacuum, or towards a maximally mixed state, an infinite temperature state. So the decoherence can either cause the system to cool off or heat up. In the models in which the system cools off and converges towards a system that looks like the vacuum, a state that looks like the vacuum, what typically happens is microscopic causality is not strictly satisfied. There is some signaling outside the light cone in the theory. but those effects can be suppressed at long distance exponentially by some mass scale. And I don't really understand this class of theories very well or how they behave, but I think I'm curious whether a model that could be described as a kind of noisy standard model is possible, which looks at long distances like the usual standard model of particle physics excluding gravity, but which has some intrinsic decoherence which decays away at long distances. So what I've been suggesting is that there's sort of an interesting convergence of ideas which is inviting us to think a little bit more deeply about whether there are alternatives to standard quantum theory. Part of that, boy, this thing is popping up all over, is, let's see, well, I don't know. So part of that is coming from the puzzles regarding the inside of black holes, which, as Joe told us, are still deeply confusing. But also, advancing technology is making it possible to do unprecedented tests which probe for deviations from standard quantum theory. We might draw some guidance and inspiration from the developing theory of symmetry-protected phases and also from the theory of quantum error correction. So a pragmatic vision for the next few years is to try to understand a little bit better what types of models with intrinsic decoherence might make sense. And the most likely outcome is that we'll fail, but for interesting reasons, which will give us some deeper insight into why quantum mechanics has to be the way it is. A less likely but intriguing outcome is that viable models with emergent quantum mechanics can be found, possibly even with experimentally testable predictions, and possibly providing some new insight into how to think about black hole quantum physics. Okay, thanks for listening.
Questions? Lenny?
Yeah, so John,
Wait.
I assume that the models, that the equation you wrote down with S's and dollar signs and things was essentially of the same type as adding random noise to a, okay, let's call it the BPS theory or whatever,
yeah.
From a long time ago. How does what you're saying get around the problem that if at tiny, tiny distances, there are huge violations of energy conservation? How do you get around that at the large distance world? I mean, if particles are being made at tiny, tiny different distances, which are Planckian or near Planckian, why don't they roast you when they hit you?
Well, there are versions of this theory in which the operators occurring in that, are
non-local.
The jump operators describing the decoherence really are operators that cause loss of energy but not gain of energy. The theories of that type have this.
These must be very non-local.
Well, it's non-local, and that's what I meant when I said there are limits or violations of microscopic causality, and there's signaling outside the light cone. But the signaling can be small at large distances. It's controlled by a mass scale in the theory.
Okay, if that's true, it's extremely interesting.
Yeah.
I have a question. Is the when you discuss the possible modifications to the quantum mechanics, is it motivated by some evidence like we see in black hole or something that tells me that there should be such modifications, or is it just discussing possibilities of having these?
Right. Well, I don't wish to claim a very direct connection between the different items on this list, which I say are motivating us to think a little bit more broad-mindedly about whether quantum theory should be exact. I'm only saying that from different points of view, at least my willingness to entertain that standard quantum mechanics is not an exact description of nature has, and my eyes are more open to the possibility than they were a few years ago for a variety of different reasons. But look, I think just the second reason is already a good one for thinking about this problem. there's a lot of very interesting and impressive experimental activity aimed at trying to amplify quantum effects to larger systems. What's the fundamental reason for wanting to do that? Well, I think that the best motivation for doing it is the one I mentioned in passing, that the separation between quantum and classical complexity, that we think highly entangled quantum systems can do things that we can't simulate in the classical world, and so it's really a new frontier of physics in that respect. But if we're looking for something fundamental, we should be looking for quantum mechanics to fail, and the question is, if it fails, in favor of what? Or what can we say from doing experiments, like, say, scaling up quantum computers, about how that constrains possible deformations away from quantum theory?
More questions? Okay, if no more, oh, yeah.
So, I made a small distinction between modifying sort of the equations and modifying the interpretation. I mean, I guess you're mostly focused upon modifying the equations in some sense.
Well,
is there when you modify the equations, does the interpretation still work?
Right. There are conceptual issues that are raised once we start fiddling around with quantum mechanics. But I don't know that we really have to turn our worldview upside down. And this is why I gave the example specifically of small amounts of intrinsic decoherence at short distances. Quantum mechanics would be an emergent property in that sense. It would be the infrared fixed point of the theory. And so the things we know and love about the interpretation of quantum mechanics are properties of that fixed point. But if we can say something sensible about deforming away from it, that would be something we could try to test in the laboratory.
Okay, let's thank John again.
Thanks.